So there is a relationship between this unit impulse, unit ramp and unit step signal. Okay, in the continuous time. Okay, this relation, it's a very important question. So it's a repeated question. Okay, so this question is asked in 2018 and 2015 as a 2 mark, or sometime we have to derive this relation. It is a 8 mark question also. Okay, so but for 2 mark, how to write means the relationship between this unit step, unit impulse and unit ramp signal. It is represented as, you see, this is del of t is a unit impulse, u of t is a unit step, R of t is a unit ramp. Okay, so if you are integrating the unit impulse, we will get unit step. Okay, if you are integrating this unit step, we will get unit ramp signal. Okay, this is a one relation. Okay, and in reverse, okay, so in reverse, if you are differentiating the unit ramp, we will get unit step signal. If you are differentiating the unit step, we will get the impulse signal. So this is the relation between these three signals. So if we want to derive the ramp signal means, so we have to integrate the unit step signal. Okay, so now that is you are having unit step signal, but if you want to derive, the signal R of t means you just integrate. Okay, this unit step signal you give it to one integrator. The output of the integrator is a ramp signal. Okay, similarly, so we will derive any signal from anything. Okay, so this is the relationship between these three signals. So it's important 2 mark question. Okay, then the fourth type of signal, it is a sinusoidal signal. So already you familiar with the sinusoidal signal. Okay, so what is the mathematical expression for one sine wave? So this is the shape of the sine signal. Okay, you see, this is the sine waveform. So what is the mathematical expression for sine wave? So this is a continuous time sinusoidal. That's why x of t equal to a into sine omega t plus theta. Okay. So each sinusoidal signal is having 3 parameters. Okay. So in this, what are the parameters? You know, means a. Okay. What is a? A is said to be the amplitude of this sine waveform. Okay. A is said to be the peak amplitude of this sinusoidal waveform. And this omega. Okay. This omega. What is this omega? Means this omega is said to be the radian frequency or angular frequency. This omega is said to be 2 pi f. The omega value, you know, it is said to be the 2 pi f. F is a frequency in hertz. Omega is a frequency in radians per second. And t, so you know t is a variable time. And this theta is the phase shift. Okay, phase shift of the sinusoidal waveform. So this is a sine waveform. Then similarly, if we want to derive cosine waveform means, what is the mathematical expression for cosine signal? X of t equal to a cos omega t plus theta. It's a cosine waveform. Okay, so this is the thing. Then it is a continuous time sinusoidal signal. Next, we are going to see the discrete time sinusoidal signal. So how to define the discrete time sinusoidal signal? In the continuous time expression, instead of this small t, we have to put small n. But what is the expression? X of n equal to a sine omega n plus theta. And omega for a continuous time signal, that is for continuous time signal, always we have to use this omega. That omega we have to use. For discrete time signal, we have to use the omega as w omega. Okay, we have to use this symbol. And in this case also, this a is said to be the amplitude, omega is a radian frequency, and theta is a phase angle. Okay, so these are all the discrete time sinusoidal signals. Also, you see the graph. So the, you know, discrete time. What is discrete time? The signal is having amplitude only in particular instant of time. In the remaining instant, the signal is having no amplitude. But you see the shape of the signal. The shape of the signal is the envelope. If you are connecting this envelope means, we will get the shape is like a sinusoidal waveform. Okay, this is a discrete time sinusoidal signal. Okay, and the next signal is the exponential signal. Okay, so the exponential signal, so the continuous time exponential signal, it is of the general form x of t equal to c into e power alpha t. Okay, where c and alpha, it is said to be the constants. Okay, so depending upon the value of this c and alpha, we may relate the exponential signal as a real exponential signal and a complex exponential signal. if this constant c and this constant alpha both are real value. For example, it is a 2, 3, 4. Real value means that signal is called as the real exponential. Okay, but in this real exponential signal, there are two types of exponential signal is there. One is decaying exponential, another one is a rising exponential. What is decaying means? The signal x of t equal to e power minus alpha t. Okay, but here you see what is the function? This function, this is a exponentially that is e power minus. So e power minus means it is a exponentially decaying function. Okay, but with respect to time, if the time increases, what about the amplitude of the particular signal? It is exponentially decreases. Okay, so this signal, it is said to be the decaying exponential. There is another one exponential signal, x of t equal to e power alpha t. Okay, but e power plus alpha t. But this signal, that is with respect to time, the amplitude of the exponential signal is growing signal. So that's why this exponential is called as the rising exponential. So these are all the some standard signal. Okay, here this c value and alpha value is real. That's why it is called as a real exponential. So next one, if the c value and alpha value, it's a imaginary means we can call it as it is a complex exponential signal. But what is the standard expression for complex exponential signal means? X of t equal to e power j omega naught t. Okay, but here you see in the place of alpha, what is the term available? J omega. Okay, but j omega, it's a complex exponential signal. So if you are expanding this e power j omega naught t, we can get cos omega naught t plus j sin omega naught t. But what is mean by this complex exponential signal? This complex exponential signal, it is addition of one cosine waveform and one sine waveform. So the addition of one cosine and sine waveform, it is called as the complex exponential signal. Okay, so this is the thing. Then the next standard signal, it's a rectangular pulse. Okay, so the other name of rectangular pulse is gate function. So this rectangular pulse, it plays a very important role in communication system. Okay, so the name itself, the name, what is the name? Rectangular pulse. So the shape of this signal, you see, so the shape of this signal is like a rectangular. Okay, that's why the name is called as rectangular pulse. Okay, so you see the graph. So from the graph, so you see for the time, some minus t by 2 to t by 2, the signal is having amplitude. The signal is having constant amplitude A. Okay, for the remaining time, okay, for this minus infinity to minus t by 2, t by 2 to infinity, the signal is having not at all amplitude. Okay, so that's why this signal is called as gate function or rectangular pulse. Okay, so what is the standard notation of this rectangular pulse means? A rect of t by t. Okay, this is the notation. That is the sine waveform is noted as sine omega t. Okay, similarly the rectangular pulse is noted as rect of t by t. Okay, A is said to be the amplitude of the rectangular pulse, and t divided by t is a variable time. Okay, divided by the capital T. What is the capital T means? It is the width of the rectangular pulse. Okay, you see. So in this pulse, what is width? The width is said to be the difference between this upper